Good day, this is Professor Arnold, and today I'm going to discuss normal distribution as an approximation to the binomial distribution. To help understand this concept, I will give you an example. Before doing so, let's review the binomial probability distribution. A binomial probability distribution has a fixed number of trials that are independent, trials that have each classified into two categories, commonly referred to as success and failure. And finally, trials with property that the probability of success remains constant. Let's take a look at some notation. We need notation because ultimately we're going to come up with a formula or a function in the calculator that we're going to use to calculate the required probabilities. So we're going to let n represent the fixed number of trials. Let x, or little x, be the number of successes in n trials. We will let p be the probability of success in one of the trials, and q, which would be the complement of p, which would be 1 minus p, the probability of failure. So we have n, x, p, and q. Make a note of those: n, x, p, and q. What are the key concepts? Let's talk about the requirements first for using a normal distribution as an approximation to the binomial distribution. One of the conditions is that we must have that np. Remember, I asked you to write down n, p, q, x. So n, which is the sample size, multiplied by p, which is the probability of success, must be greater than 5, greater than or equal to 5. Similarly, nq must be greater than or equal to 5. The normal distribution is a continuous distribution, whereas the binomial is discrete. So we need to have a way of using the variables that we use for binomial, which are usually n, p, q, x. We have to make a transformation from that to the normal distribution. And the way we do that is by calculating mu and sigma. Mu is the mean, which is going to be used by the normal distribution, but we don't have it readily from the binomial. We have to make a calculation, and that calculation is mu is equal to np. Similarly, sigma is equal to the square root of n times p times q. So these two figures are what you're going to need to write down. You need to find mu and you need to find sigma, and they are given as follows: mu is equal to np and sigma is equal to the square root of n times p times q, square root. Like I said before, the binomial probability distribution is discrete. So that is, we deal with whole numbers for the random variable. On the other hand, the normal approximation is continuous. To compensate for this, we use something that is called a continuity correction. In other words, we have a whole number x in the binomial probability distribution, and we need to turn that into an interval on the normal distribution. And that's easy enough. We make an interval by backing off 0.5 to the left and going to the right 0.5 from x. So that gives us the interval x minus 0.5, x plus 0.5. So we need some more examples of continuity corrections, because when you come to do a problem, it's not always going to be find the probability that x is equal to some number. It's either going to be x greater than some number, x less than or equal to some number, and so on. So what I'm going to give you here is a list of continuity corrections that I think would cover every case that you're going to come across. So on the left side, I'm going to show you a statement about the discrete variable, in other words, the binomial. And on the right, I'm going to give you the statement, the equivalent statement that we have to make for the continuous normal distribution. So again, if we have exactly a number, such as 1 or 2, on the normal side, we would use an interval between 0, 1, or 1.5 and 1 or 2.5. Let's look at least 1 or 2. This includes 1 or 2 and above. So on the normal side, we would look at everything to the right of 101.5. More than 102. This time, this does not include 102. So we want to go to the right of 102.5. At most 102, this includes 102 and above. So on the continuous side, what we look to the left of 0.2.5. At most 102 includes 102 and below. So on the continuous side, we look to the left of 102.5. And then finally, we have fewer than 102. This doesn't include 102. So you go to the left of 101.5. So we're ready now to do an example. Here's the example. Based on a cell phone survey, assume that 54% of adults with cell phones use them in restaurants. In a separate survey, 210 adults with cell phones, it is found that 99 use them in restaurants. If the 54% rate is correct, find the probability of getting 99 or fewer cell phone users who use them in restaurants. Use the normal approximation binomial technique. Here are the steps to doing this problem. There are 4 steps. First, we check that the requirements are met. Secondly, we look at what are the preliminary values. The preliminary values are the mu and the sigma that we talked about earlier. Make the continuity correction. That's that table that I showed you that you need to make a note of. And then finally, we'll make the computation to find the required probability. Let's look at step 1. We're going to check the requirements, right? So NP must be greater than or equal to 5, and that is 210 times 0.54, which is 113.4, so that's greater than 5. Similarly, NQ is 210 times 0.46. Multiplying that out, we get 96.6, which is clearly greater than 5. And then we get ready to go on to the next step, which is to determine the preliminary values. So we're going to find mu. So mu is the NP, which is 113.4. Sigma is the square root of NPQ, so we're going to substitute. And I get the square root of 52.164. Now I'm going to leave it like that because the next time I use it, I'm going to use it in a function. And that function is on the calculator. And that function is capable of doing simple operations such as the square root. So all we have to do is make a note of it. So I'm going to make a note of it. Mu is 113.4 and sigma is the square root of 52.164. Please write these down. Mu equals 113.4. Yes. Sigma equals square root 52.164. Yes. Okay. So now we're going to make the continuity correction. We are asked to find probability that x is 99 or less. So this includes 99. So we adjust it to probability of x less than 99.5. So we're going to go to the next step. We're going to still need two values. So I'm going to write them down. And then we go to step 4. And we're going to use the TI-84 or the TI-83 calculator. And we're going to find that on the calculator. Let me bring up the calculator so you can see that. Here we go. The second key is the blue key. So you press that, then you press var, which is over there on the third row and over to the right. And the function you're going to use is what I show up at the top, normal CDF. Now this normal CDF requires 4 variables, 4 input values. So I'm going to enter in the input values, and there are, we're going to put in from -infinity to 99.5, and we need to put in an approximation there. So we put -1e99, comma 99.5, and it also requires the mu and the standard deviation. Otherwise, it's going to think that you are giving it z-scores, and these are far from z-scores. So it's -1e99, comma 99.5, comma those two values that we've been carrying around, which is 113.4 and the square root of 52.164. This is just another way of writing the square root of 52.164. 52.164 raised to the 0.5. So we're going to plug that into the calculator. Let me show you that here. See, I have them plugged in on the right side. I'm using a TI-84, and this is what it would look like. And then you see your value comes out 0.02714, and we round that to 4 places of decimal, which would give me 0.0271. And there is the end of. Okay, so this is the end of the presentation. If I went fast in certain areas, go back, play it again, pause it at certain places where you had difficulty. Make sure you have your calculator with you during the presentation. Thanks for watching.